In example 5, we've got a morning commute, so maybe this is you driving to work in the morning or driving to school in the morning. It's a random variable, apparently, that has a beta distribution with alpha and beta both being 2. And this is measuring your commute in hours. So remember, y is always between 0 and 1 in the beta distribution. So I guess that means that your commute could be 0 or it could be up to an hour. In part A, we're going to find the chance that it will take longer than 30 minutes. So what we'll actually be looking for there is the probability that y is bigger than or equal to, 30 minutes is 1/2 an hour, so it's bigger than or equal to 1/2. And in part B, apparently you have a range level, which is a function of how long your commute is, and we want to find the expected value of range that you will arrive at work with tomorrow. So let's work this out. The first thing I'm going to do is try to identify the density function for this distribution. So we've got f of y. The generic density function for the beta distribution is y to the alpha minus 1, 1 minus y to the beta minus 1, divided by b of alpha beta. Let me go ahead and find the value of that constant, b of alpha beta. I think the easiest way to calculate these, if you have whole numbers, is to convert it into gammas. So let me convert that into gamma of alpha times gamma of beta divided by gamma of alpha plus beta. That's the formula that we learned back on one of the first slides in this lecture. So in this case, we've got gamma of 2 times gamma of 2 divided by gamma of 4, because alpha and beta are both 2. That was given in the problem. And so this is 1 factorial times 1 factorial. Now, gamma of 4 will be 3 factorial. Remember, the whole point, well, part of the point of the gamma function is it's sort of a generalization of the factorial function, but it is offset by 1. So gamma of 4 is 3 factorial. 1 factorial is 1, 3 factorial is 6, so this is 1/6 here. Now, this f of y is y to the alpha minus 1, so that's y to the 1. 1 minus y to the beta minus 1 is also 1. And now we know that we're dividing it by 1/6. So this simplifies down into 6. Y times 1 minus y is y minus y squared. Let me go ahead and distribute that. 6y minus 6y squared. So that's my density function for this distribution. We're going to go ahead and use that to solve these two problems. I'm going to jump over onto the next slide and use that density function to solve these two problems. But let me recap where these came from. First, I was writing out the generic density function for the beta distribution. So there's the formula there. I had to figure out what b of alpha beta was. So I did that down below. I converted that into a bunch of gammas because I know easily how to solve the gamma function when you have a whole number in there. It's just the corresponding factorial, except you have to shift down by 1 to figure out to plug a number into the factorial. So that's why b of alpha beta turns out to be 1/6. So I plugged that into my density function, and I also plugged in the values of alpha and beta. So 2 minus 1 is 1. And so I got 6 times y minus y squared. So that's the density function that I'm going to work with in order to solve these two problems. Remember, on the next page, I'm not going to copy the problems because I'll need the space. We're going to solve the probability that y is greater than 1/2, and then we're going to find the expected value of r. Those are the two things we're going to solve on the next page there. So we're still working on example 5. We had the setup on the previous slide, but what we figured out was the density function is equal to 6 times y minus y squared. And now for part A, we wanted to find the probability that your commute will be longer than 30 minutes. So the probability that y will be bigger than or equal to, we're measuring things in terms of hours. So I converted 30 minutes into an hour. It's 1/2. And so that's the integral. Remember, our range is from 0 to 1. So 1/2 to 1, because we want it bigger than 1/2, of 6y minus 6y squared dy. And now we have a little calculus problem to solve, and it's not a hard one at all. So that's, let's see, integral of 6y is 3y squared. The integral of 6y squared is 2y cubed. And we want to integrate that, to evaluate that from y equals 1/2 to y equals 1. So that's 3 minus 2 minus 3 times 1/2 squared is 3/4. And now plus 2 times 1/2 cubed. 1/2 cubed is 1/8. 2 times 1/8 is 1/4. So we get 1/4 there. And so 3 minus 2 is 1, minus 3/4 is 1/4. So this is 1/4 plus 1/4. And so that's 1/2. That's the probability that you're going to spend more than 30 minutes in traffic tomorrow morning. For part B, we had this rage level. Your rage level was r is equal to y squared plus 2y plus 1. And what we wanted to calculate there was your expected rage level. How angry are you expected to be when you get to work? So what we're going to use heavily here is linearity of expectation. The expected value of r is the expected value of y squared plus 2y plus 1. But that's equal to the expected value of y squared. This is using linearity now. Plus 2 times the expected value of y plus, we can say the expected value of 1, but the expected value of 1 is just going to be 1. And so now I need to find the expected value of y and y squared. And in order to figure out those, I'm going to remember what we learned on one of the very early slides. So you can flip back, and I think the slide was called Key Properties of the Beta Distribution. What we learned was that the expected value of y was equal to alpha divided by alpha plus beta. And in this case, alpha and beta are both 2. So this is 2 divided by 2 plus 2. So that's 2 divided by 4 is 1/2. Now that was the easy one. The expected value of y squared is a little trickier. And what we're going to do is use the variance. So sigma squared, and that was kind of a complicated formula. Let me remind you what it was. This is coming from, I think it was the third slide in this lecture. It was called Key Properties of the Beta Distribution. Alpha plus beta quantity squared times alpha plus beta plus 1. So we're going to work that out. Alpha times beta. Remember, alpha and beta are both 2. That was given to us on the previous slide. So 2 times 2 is 4, divided by 2 plus 2 squared is 16, and then 2 plus 2 plus 1 is 5. So this is 4 divided by 16 is 1/4, times 1/5 is 1/20. Now, that is not the expected value of y squared. That is the variance. But let me remind you how we used to calculate the variance. That's the expected value of y squared minus the expected value of y quantity squared. What we can do is we can use this to solve for the expected value of y squared. That's kind of an old trick in probability, is if you know the variance, you can sort of reverse engineer for e of y squared. So e of y squared is equal to 1/20 plus e of y quantity squared. And now we can write that as 1/20. We figured out what e of y is. It's 1/2. We figured that out up above. So 1/2 squared. So this is 1/20 plus 1/4, which is, my common denominator there is 20. 1 over 20 plus 1/4 is 5/20. So I get here 6/20, and that reduces down to 3/10. And so my range level, remember I decomposed it into e of y squared plus 2e of y plus e of 1. Now I can solve that. E of r is e of y squared plus 2e of y plus 1. I can solve that. E of y squared is 3/10. 2e of y is, what is it? 2 times 1/2. And, well, I should have written e of 1 up above. There's e of 1. But e of 1 is just 1 because that's the expected value of a constant. Well, a constant is always going to be a constant, so it's 1. So this is 3/10 plus 1 plus 1. So 3/10 plus 2 is 23/10, otherwise known as 2.3. I don't know what the units are there, so I'm just going to leave them. I guess 2.3 rage units is what you're going to carry into work, or at least the expected value of your rage as you go to work tomorrow morning. So 2.3 is the expected value there. So that answers both things that we were looking for here in this problem. Let me remind you where everything came from. This f of y, this density function, is something we figured out on the previous slide. You can check back on the previous slide and you'll see all the steps calculating that. In part A, we had to find the probability that it will take longer than 30 minutes to drive to work. Well, 30 minutes is 1/2 an hour, and we want it to be longer than 30 minutes. So we're going to integrate from 1/2 to 1, the density function, and that turns out to be a fairly straightforward integral as long as you keep the fractions straight. And we get that the probability there is exactly 1/2. So half the time your commute will be longer than 30 minutes, half the time it'll be shorter than 30 minutes. In part B, we had to find the expected value of your rage level, where it's defined like this. So the expected value decomposes into these 3 terms. That's using linearity of expectation. Very, very useful for this kind of problem. The expected value of y, I'm looking up the formulas for mean and variance on an earlier slide from this talk. If you go back, if you scroll up, you'll see a slide called Key Properties of the Beta Distribution, and that's where I got these formulas, these complicated formulas using alphas and betas. But then I just plugged in alpha equals 2 and beta equals 2. That was given to me in the problem, and simplified those down into fractions, 1/2 and 1/20. However, this was the variance. It was not the expected value of y squared directly. Remember, the old way to calculate variance is to find the expected value of y squared minus the expected value of y quantity squared. And so what we can do is sort of reverse engineer this in order to solve for the term we want. Well, here it is. The term we want is the expected value of y squared. So I bring this e of y squared over to the other side, and that's where I get 1/20 plus e of y squared. And then this half right here is that half right there. So that's where that half comes from. And then it's some more fractions, doing a little simplification of the fractions. We get that e of y squared is exactly 3/10. Drop that in to our expected value for r, and then this 1/2 is also that 1/2 from the e of y, and the expected value of 1 is always 1 because 1 is constant, so you expect it to have its value. And then simplifying down, 3/10 plus 1 is 23/10, or 2.3. So that wraps up this lecture on the beta distribution. This was the last of the continuous distributions. We've worked through the uniform distribution and the normal distribution and the gamma distribution. The gamma, of course, includes the exponential and the chi-square distribution. So we had one big lecture on all of those. And now finally we've got the beta distribution. So you're supposed to be an expert now on the continuous distributions. We've got one more lecture in this chapter. It's going to cover moment generating functions. functions. So that's what you'll see if you stick around for the next lecture. In the meantime, you have been watching the probability lectures here on Educator.com. My name is Will Murray. Thanks for joining me today. Bye-bye.